In this video, we look at the cross product. The cross product is between two three-dimensional vectors, and we are going to define the cross product. We will then quickly look at the determinant because that will segue us into a formula to finding the cross product of two vectors, and then we will use the cross product to do a couple problems. If you are following along in the textbook, we got page 862 to 867, 862 to 867. But yeah, this video is an intro to the cross product. Let's get started. So before I jump into the cross product, I want to remind you what the dot product was. Right? So the dot product of two vectors, let's go with A, B, C, dotted with D, E, F. The dot product was a scalar value. It was a single number. This was A times D plus B times E plus C times F, right? And that equals a number, a scalar quantity, right? Some quick other things about the dot product. The value was the magnitude of the first vector. So let me go ahead and give these names U and V, right? This scalar quantity was also the magnitude of U times the magnitude of V times the cosine of the angle between them. That is what the dot product's magnitude was. So if you know the magnitude of this, you know the magnitude of this, and you know the angle between them, this was the scalar quantity. Now, this conveniently was equal to this value. All right, so moving past that, the cross product is going to be defined similarly. When we defined the dot product several weeks back, we defined it as having this magnitude. We are going to define it having a specific magnitude, but before I get to that, the cross product of two vectors, U and V, written like this, U cross V, is, first off, it is a vector. Right? The dot product was a scalar. I've said this several times now. The cross product is not going to be a scalar. It's going to be a vector. Right? Sometimes people call the cross product the vector product, and the dot product is sometimes called the scalar product. The cross product is a new way to multiply two vectors, right? To take the product of two vectors, but the result is a vector, not a scalar quantity. Let me emphasize that. The cross product outputs a vector. This vector, additionally, let's call it U cross V. U cross V is going to be perpendicular. All right, I probably should write that thing out. Right, perpendicular to U and V. So you might already start to brainstorm reasons why being able to take the cross product between two vectors is going to be a useful tool. All right, U cross V is going to be perpendicular to U and V. If you have two vectors and you want a vector perpendicular to them, this product, which we're going to learn how to do, is going to give you a perpendicular vector to the two given vectors. With that said, U cross V perpendicular, that vector is going to be perpendicular in a specific direction. If you have two vectors, let me go ahead and sketch them here. Right? If you have the cross product between two vectors, that vector, when you take the cross product, is going to follow the right-hand rule. Follows the right-hand rule. Well, if I were to take a vector here U and a vector here V, there are two directions that are perpendicular to both of these vectors. There's this vector that I've drawn going up, and there's another vector that I could draw going down that is also perpendicular to U and V. Right? We want to specify which one of those two directions we are going in when we take the cross product. And what I mean by the right-hand rule is if you take the first vector and you point your pointer finger in the direction of it, pointer finger. And then you take your middle finger and you point your middle finger in the direction of the second vector. Your thumb is going to point in the correct direction for the cross product. But if you do this process with your right and left hands, this vector that your thumb points in is going to be different. One is going to be pointing up here, and one is going to be pointing down, right? We follow the right hand rule, so you must do this process with your right hand, right? And that's just convention. This could easily have just been defined using the left hand rule, but we use the right hand rule. That is what it ultimately is going to boil down to. So take your right hand, point your pointer finger in the direction of the first vector, point your middle finger in the direction of the second vector, and the direction that your thumb points is the direction of the resulting vector u cross v. All right, something that might be popping into your head right now is whether or not u cross v is commutative. Is u cross v equal to v cross u? And I'll let you think about that for a second. And you know what? I'm going to let you think about that for more than a second. We'll come back to that. Right? But we have a vector. U cross v is perpendicular to those two vectors. The resulting vector follows the right-hand rule. And finally, what's that magnitude? The magnitude of u cross v is going to be the magnitude of u times the magnitude of v, very similar to the dot product, but instead times the sine of the angle between them. All right, this has some immediate physics properties. Real quick, physics. If you think back to physics, what was u, v, sine theta? What was a number times the sine of the angle between them? That was torque. So this is used a lot in physical applications, mechanical physics, and other things too, don't get me wrong. All right, but that's something that you've done before, so I wanted to bring torque up. But okay, so we have the dot product. It is a number, and it tells you how much work is being done given to vector quantities. But that the cross product, it outputs a vector. That vector is perpendicular. In which direction is it perpendicular? It follows the right-hand rule. Right, you point in the direction of the first vector with your pointer finger. Your middle finger points in the direction of the second vector, and your thumb is going to point in the direction of the new vector. And then the magnitude of this vector is going to be uv sine theta, or mag u mag v sine theta. Let's go ahead and figure out how to get a vector that does all of these things. That is a tall order. So let's figure this thing out. So I got myself a new page here. And what I want you to do is I want you to take the cross product of some very simple vectors, I, j, and k. I want you to take the cross product of these. This is a little bit more doable. Right? You can just find a vector that satisfies all four of my bullet points with I and j. And the first thing that's easy to figure out is the direction. So I cross k, if you point your finger in the direction of I, right, we have a 3D graph here. Let me go ahead and get that sketched. Cool. If you take your pointer finger and point it in the direction of I, you take your middle finger and you point it in the direction of j, then the resulting vector is going to be the direction that your thumb points, which is in the direction of k. So I cross j, we don't know its magnitude yet, but we do know its direction. It's in the direction of positive z. It's in the k direction. Right? What is its magnitude? Well, its magnitude, so let me say this real quick. It has no I or j component. A vector in the I direction crossed with a vector in the j direction is going to only have a k direction. So there is no I or j component. So what's the magnitude? It's the magnitude of I times the magnitude of j times the angle between them. Well, what's the angle between I and j? That's a 90-degree angle. That's a pi over 2. So we have the magnitude of I, which is 1, times the magnitude of j, which is 1, times what is the sine of 90? That is 1. All right? So I cross j is just the vector k. Right? 1 times 1 times 1 is 1, and then 1 times k, that's just the vector k. So I cross j is k. All right? Let's look at what j cross I is. What's j cross I? Well, j cross I, right? If you point your pointer finger in the direction of j, and you point your middle finger in the direction of k, instead of pointing up, we are going to be pointing down. So we are going to get a vector in the negative k direction. So we're going to have a negative value here, and we're going to go in the negative k direction, the negative z axis, right? But similarly, we still have a 1 times the angle between them is still 90, so we have 1. So j cross I isn't k, it's negative k. And earlier I had mentioned, is I cross j, is u cross v commutative? No. I cross j is k, j cross I is negative k. These are not the same value. I cross k. I'm going to go ahead and add this right at the top of the page here. All right. Note, I cross j does not equal j cross I. Right? So keep that in your brain. So we are using the right-hand rule and just some simple unit vectors with magnitude 1 to establish some basic facts about the unit vectors. And I'm going to go ahead and write them all down here. You can go ahead and think about them yourselves. If you like cross j, what it was z and I, what are you going to get? You can think about that. But I'm just going to go ahead and write all these down at this point. I cross j was k. J cross I was negative k. I cross k, that is going to be negative j. I'll let you think about that. All right. If you point in the direction of I with your pointer finger, point in the direction of x, point in the direction of z with your middle finger, your thumb is going to point in the negative j direction. All right. But conveniently, k cross I, that's going to be positive j. All right. Lastly, we have j cross k, which ends up being positive I, and k cross j, which ends up being a negative I. Okay, we're going to use these in a second. There are a few more that we don't have. All right. What is I cross I? Well, there are lots of vectors that are perpendicular to I, but the angle between I and I is 0, and the sine of 0 is 0. So I cross I is 0. It's the 0 vector. All right. J cross j. Similarly, the angle between identical vectors is 0, and the sine is 0. And k cross k, that's going to go ahead and also be 0. So we have these 9 introductory cross products. Right. The goal is to be able to take A, B, and C and cross it with D, E, and F, which is a more complicated question. But we can easily do it with these unit vectors. We have done that here. But we are going to use these to figure out what that is. All right, it's time to do it. So let me go ahead and do a new page. And I want to cross x1, y1, z1, in other words, vector 1. I want to cross that with vector 2, x2, y2, z2. This is my goal, to figure out what this is. All right, so now we need to figure out how can we connect this simple question, crossing the unit vectors, with crossing this more complicated set of vectors? Well, don't forget that every vector can be written as the sum of a certain amount of unit vectors, right? If this was a 3 right here, really that's just 3 i's, right? So let me backtrack. This first vector can be written as x1 times the vector I, y1, not comma, but plus y1 times the j vector plus z1 times the k vector. And then over here, we can write this vector as x2 times the I vector plus y2 times the j vector plus z2 times the k vector. Right? We are boiling this more complicated question down into a unit vector question, which we know how to do already. All right, to figure out what this thing is, let's distribute. All right, we are going to look at the cross product of every combination of the elements of these two vectors. So we're going to have x1i and cross with x2i. But we're also going to look at x1i crossed with y2j and x1i crossed with z2k. I'm going to keep going, but I'm going to go down a line because I see that I'm going to run out of room. I'm going to have 6 more terms. I'm going to have plus y1j crossed with x2i. I'm being very careful to maintain my order. All right, the one vector is always coming before the two vectors because we already established that these are not commutative. All right, if we start switching the order, we'll get the other vector. It's as if we would have switched the original two vectors. All right, I'm going to continue. We're going to have y1j crossed with y2j. And then we're going to have y1j crossed with z2k. All right, I'm going to go down to the next line. Plus, what's the last one? z1k. We're going to cross that with x2i. We're going to have z1k crossed with a y2j. And then we're going to have z1k crossed with z2k. All right. What is this thing? This right here is the cross product of these two vectors. But let's clean this thing up because I have a feeling that it's going to simplify. But that's just me talking. All right, so what is x1i cross x2i? Well, these two vectors are in the same direction. The angle between them is 0, and the magnitude of these two vectors is going to be the magnitude of the first one, x1, times the magnitude of the second one, x2, times the sine of 0, which is 0. So x1i cross x2i, that's just going to be 0. All right, this is already simplifying. All right, x1i cross y2j, what's that going to be? Well, the magnitude will be x1 times y2, but the direction is going to be I cross j. What was I cross j? I cross j was k. And multiplying this by the vector k, let me remind you, doesn't change the magnitude because the magnitude of k is 1. It is a unit vector. Right? Continuing along, x1i cross z2k, its magnitude is going to be x1 z2, right? The magnitude of the first times the magnitude of the second, and it's going to follow the right-hand rule. What's I cross k? Where is it? I cross k is negative j. All right, so I actually need to break out the eraser here. If you're following along in your notes, sorry about that, but it's always good to have an eraser on hand. All right, minus j. So it's going to be the magnitude of the first vector times the magnitude of the second vector times negative j, because I cross k is negative j. All right. Let me go ahead and put a dashed line here because we're going to continue. y1j cross x2i, that's going to be y1 times x2. That's the magnitude of the first times the magnitude of the second. And then j cross I, order matters. J cross I, where are you? J cross I is negative k. So I'm going to have to put a negative k there. All right, I'm going to keep going. All right, y1j cross y2j, same direction, angle between them 0. The sign of 0 is 0. That's going to be a 0. And then over here, y1 z2 is the magnitude. And then j cross k, you can break out your right hand and point your fingers in the appropriate directions, or you can just go back in your notes. J cross k is I. J cross k is in the positive I direction. And this last one I'm going to do real quick. It's going to be plus z1 x2. K cross I is positive j. And then we have k cross j, which ends up being negative I. And the magnitude here is going to be z1 y2. And then k cross k, no matter the magnitudes, is going to be 0. All right, I'm going to take this like square equation here, or this square expression, move it to the next page. So we had a bunch of zeros, but what was left over, right? Let me actually back up. x1, y1, z1 crossed with x2, y2, z2 ends up being equal to x1, y2, k minus x1, z2, j minus y1, x2, k plus y1, z2, I plus z1, x2, j minus z1, y2, I. Let's continue to clean this thing up because we got some terms with constants that we can, sorry, not constants, these terms have the same direction vector. We can group them. So let's go ahead and put I first. So let me find all my I's. I got a y1 and a z, I didn't write z2, but I should have, z2. And I have a minus z1, y2. All right, that is my I vectors here in the cross product of these two vectors. All right, then I have a plus where are my j's. My j's are right here, z1, x2. And I have and my other j's right here, minus x1, z2. Notice that the same letters are popping up. That's convenient. Then I'm going to have, in my k's, I have x1, y2. And I'm going to guess I'm going to have a minus y1, x2 because I know I see a pattern happening here. And where is it? It's right there, z1, where is it? y1, x2, y1, x2. Cool. Awesome. All right, so there is a more simplified cross product. We have the cross product. Don't get me wrong. We just want to make it nicer. I'm going to do one last thing that I will justify later in this video. But see how we have a yz, zy, and an xy, yx, right? This one, we don't have that alphabetical nature. We have zx, xz. I want this to be alphabetical. I want the x to be the leading term. So I'm actually going to factor out a negative. Like, this might seem bizarre, but it's going to make sense in terms of an algorithm for figuring this out. I'm going to have a minus x1, z2 minus z1, x2 times j. Go ahead and verify that these two things are the same. And then down here, I still have that alphabetical nature, so I'm happy over here. I do want to write an X and not a Z though. Cool. All right, there it is. This is the formula. It is cumbersome. It is nasty. It is hard to remember, which helps me segue into the next just quick topic. I'm going to give you a way to calculate the cross product of two vectors using something called the determinant, which I'm going to look at on the next page. All right, so the determinant. In relation to matrices. All right, so I'm throwing a lot of new things at you real quick, but it's not too important that we understand this stuff now. You will deeply understand this stuff later. Right? What I need you to know is if I take an array of numbers, A, B, C, and D, in this case, I have a 2 by 2 array of numbers. Right? The determinant of this matrix, I'm using square brackets to be technical, right? The determinant of this thing is written as the determinant of the matrix A, B, C, D, all right? And it's often given the notation of bars without brackets, just vertical bars, A, B, C, D. Right? The determinant of this is this leading diagonal, the product of this leading diagonal, AD, minus the product of this diagonal in the opposite direction, BC. Right? That is the determinant of this, what we call a matrix. Right? The determinant of something a little bit larger A, B, C, D, E, F, G, H, I, the determinant of this larger matrix, the determinant of this thing, is going to look very similar to what we just derived the cross product to be. What I'm going to do to calculate the determinant of this matrix is I'm going to start with this term A. Right? And what I'm going to do is I'm going to take the term A and I'm going to multiply it by the determinant of the submatrix, the one that is left over when I get rid of the entries beneath and next to A. So if I have the term A here, I'm going to multiply it by this leftover 2 by 2 matrix, E times I minus F times H. Then I'm going to take, so let me go ahead and write A, B, C, D, E, F, G, H, I again. I'm going to take this second column and I'm going to delete it. I'm going to delete the terms next to B, and I'm going to multiply that thing by the determinant DI FG minus DI FG. When doing this algorithm, I'm going to go ahead and get rid of this B down here. When doing this algorithm, we put a minus right here, which will become apparent later when you're in Precalc C. But we have EI minus FH times A minus DI minus FG times B. And the last one is going to be, if I were to do that with the final column, CFI and ABC. If I were to get rid of those, I'm going to take the term C and multiply it by the determinant of this leftover 2 by 2, which would be DHGE. DH minus EG. Cool. That is the algorithm for finding the determinant of a matrix. Right? We are deleting columns and rows and then finding the 2 by 2 determinant of what is left over. Right? We can use this when we are determining the cross product of two vectors, and this is how we do it. All right, what I'm going to do is I'm going to take those two vectors, x1, y1, z1, and x2, y2, z2. And I'm going to take the determinant of the following matrix. In my top row, I'm going to have I, J, and K. All right, in my second row, I'm going to have the first vector. And please keep in mind that the first vector must go in the second row. You can't put it in the third. As we talked about earlier, vector cross product of the vector product is not commutative. And in the final row, we're going to have x2, y2, z2. And we are going to take the determinant of this matrix. The determinant of this augmented matrix is going to be the cross product. All right, I'm going to take the entry I. I'm going to delete the column and the row that it sits in. And I'm going to take I, and I'm going to multiply it by the leftover determinant, y1, z2, and then z1, y2, minus z1, y2. Right? Then the next one, you got to remember to put a minus here. It's kind of annoying. Right? This will become clear when you start to do determinants in matrices in the matrices unit. All right. We're going to have the J column and the J row are going to get deleted, and I'm going to be left over with x1, z2 minus z1, x2. And I'm going to multiply this by negative j. And the final one, I'm going to delete the k column and the k row, and I'm going to be left with x1, y2 minus y1, x2. And if you notice, this thing that we call the determinant of a 3 by 3 array of numbers, a matrix, is the cross product. This is equal to what we had on this page right here, y1, z2 minus z1, y2, I, minus x1, z2 minus z1, x2, j, plus x1, y2 minus y1, x2, k. That is what we have here. And that is how we find the cross product of two given vectors. We create this 3 by 3 array of numbers, and we use this algorithm. All right, this video is not about explaining why this algorithm is a thing. All right, that will come later. All right, this video is talking about how this algorithm computes what we proved over here, what the cross product of two vectors is. Here we just use the definition of what the cross product is. Over here, this value is conveniently the same, this determinant. And this is also nice practice for when you actually learn the determinant later and you learn its theory. You're going to already know this algorithm, which is nice. All right, that is enough theory. Let's go ahead and actually use this in practice. I think that is where you start to really understand how this algorithm and how we find this cross product, this perpendicular vector. So here are two vectors. I have 6, -3, 3. And we're going to cross it with 4, 9, -7. Right? Our final answer better be perpendicular to these two vectors. Think about how you can verify at the end whether or not these two vectors are perpendicular. Or sorry, the result is perpendicular to these two vectors. Right? And then it also needs to have magnitude uv sine theta. So you don't have to do this every time, but in this problem at the end, we're going to verify those two things. Does it have the correct magnitude, and is it perpendicular to these two things? So I'm going to now create my 3 by 3 array of numbers, what we call a matrix. The first column is the first row is going to be I, J, and K. The second row is going to be the first vector, and the third row is going to be the second vector, 4, 9, -7. And we're going to compute this, what we call determinant. So we're going to have an I times -3 times -7, that's 21, minus 9 times 3, that's 27. We'll simplify this in a second. right? The most annoying part about this process is remembering the negative on the j term. We have 6 times negative 7, that's negative 42. And we have 3 times 4, that's going to be minus 12. All right, 3 times 4 is 12, but we are subtracting that term. And lastly, we have an addition here, and we are going to have, what do we have? 6 times 9, which is 54. Minus 4 times negative 3, that's negative 12. So we're going to have minus negative 12, that is plus 12. So we'll account for that in this next line. So 21 minus 27, that is going to be negative 6i. All right. Negative 42 minus 12, that's going to be negative 54, but we have a negative here, so we're going to have a positive 54j value. And then over here, we're going to have 54 minus negative 12, that's going to be plus 12, that's going to be 66. 66k. Let's go ahead and convert this vector into its component form. We got negative 6, 54, comma 66. There we go. This is the cross product of 6, negative 3, 3, and 4, 9, negative 7. I want to verify this. Right? Is this vector, does it have magnitude, AB sine theta, and does it have direction perpendicular to the two original vectors? I'm going to go ahead and call this vector here u. I'm going to call this vector here v. This is just going to be u cross v. All right, we're not going to give it its special name. All right, and I'm going to go ahead and just calculate these values off camera so that I can just write them down. You can go ahead and verify them if you want, or you can wait to see what I get. All right, the magnitude of u ended up being 7.348 units. The magnitude of v ended up being 12.083 units. The cosine of theta is u dot v over the magnitude of u times the magnitude of v. That ended up being some number. But when I took the arc cosine of u dot v over u v, that ended up being 105 degrees, right? When I then calculated the cross product, which would be u cross v, when I calculated the magnitude, right? That was u v sine theta, and in this case, that is 7.348 times 12.083 times the sine of 105, which ended up being 85.481, right? But then when I found the magnitude of this thing, right, negative 6 squared plus 54 squared plus 66 squared, all square rooted, I also got 85.481. So the magnitude of the cross product result after this algorithm that we did has the same magnitude as what we anticipated, uv sine theta. So we're golden there. And then the next thing that we need to do is take the dot product of u and the final answer and v in the final answer, and those should be 0. The dot product of perpendicular vectors is 0. Okay, this first dot product is going to be 6 times negative 6. We have negative 36 plus negative 3 times 54. That's 162, negative 162. And then we have 3 times 66. That's 180 plus 18, 198 plus 198. And that looks like it's going to be 0. Negative 36 minus 162. That is negative 198 plus 198 is equal to 0. And then down here, all right, the dot product with the other vector and the final answer should also be 0. Let's figure it out. 4 times negative 6, that's negative 24. 9 times 54. Well, 9 times 50 is 450 plus 36. 450 plus 36, that's 486 plus 486. And then we have a minus 7 times 66. That's going to be, we got negative 42, and we have negative 420, and that combined is negative 462. All right, and then if I sum these things, you can kind of already see that it's going to work out. All right, but we have negative 24 and negative 462, which is, let me make that look more like a 6, which is negative 486. We have 486 minus 486, which is 0. All right, sweet. The dot product with the final answer, which we want it to be perpendicular, and the original two vectors is 0 for both. So we have two vectors that are 105 degrees apart, and we use this algorithm to find a vector that is perpendicular to both with magnitude u, v, sine theta, u, v, sine theta. Cool. All right, that is the cross product. All right, I want to do one last thing with the cross product, and that is given 3 points, A, B, and C, can you find the equation of a plane given 3 points? So if I have a plane with 3 points in it, A, B, and C, can I find a equation of this plane? Right? That is the question. And I'm going to give you some points. 3, 1, 4. 0, 2, negative 4. And 5, negative 2, negative 7. And this is the part of the video where I stop and encourage you to try to figure this out on your own. We have these 3 points. Right? 3 points in geometry define a plane. Can you find the equation of this plane given 3 points? And how can you use the cross product to do this? So go ahead and pause the video, but I, at this point, am going to move on. If I have 3 points in a plane, I can create 2 vectors in the plane. All right, vector AB and vector AC. That little vector here is a little bit off, but that's not the end of the world. All right, I can find 2 vectors in this plane, and as we learned in the previous video, if you want to describe a plane, you need a vector perpendicular to the plane. So we need this vector. We need what we call the normal vector. Right? This vector is perpendicular to B and perpendicular to C. Right? How can you find a vector that is perpendicular to AB and AC? Take the cross product of AB and AC. Right? And then you have your vector, and then you need a point on the plane. You're given plenty of those. We are home free. So now I'm going to proceed and do this problem. So we need vector AB. Vector AB is just the coordinates of B minus the coordinates of A. So we have 0 minus 3. We have a negative 3. 2 minus 1, 1. And negative 4 minus 4, negative 8. We're going to cross that with AC. So 5 minus 3, that's 2. Negative 2 minus 1, that's negative 3. And negative 7 minus 4, that's negative 11. We're going to cross these 2 vectors. That's going to give us this vector here. Actually, I should be careful. It's actually going to give us, let me rewind. Think about why this is true. This is a good moment. Think about why AB cross AC is actually going to give you this vector down here. All right, this vector down here, this one is AB cross AC. This vector up here is AC cross AB. All right, order matters. But for the purposes of what we're doing here, finding the equation of a plane, it does not matter. Right? We are going to get a vector perpendicular to the plane. We have a point in the plane. We will be able to get to the equation. So I am going to continue, but I'm going to do it in red so that I know I'm getting that vector going down. So we have a -3, 1, -8, and we're crossing that with 2, -3, -11. Sweet. So let me go ahead and set up my matrix. I, J, K. And then I'm going to have the first vector, -3, 1, -8, -3, 1, -8. And then down here, I'm going to have 2, -3, -11. And now I'm going to go through that process. So I'm deleting the columns and rows appropriately and then multiplying by the leftover 2 by 2 determinant. So I'm going to have an I, -11 minus 24 minus J, -3 times -11, 33 minus -16. All right, that's going to be plus at the end, but it's going to be minus ultimately because I have the minus on the J term always. And then we're going to have -3 times -3, 9 minus 2. Cool. There we go. And then I'm going to simplify this thing. -35 I minus 33 plus 16. That's going to be 49. And then 9 minus 2, that's 7. So plus 7k. And then my final vector in its component form, -35, -49, 7. All right, we are not done because this is the vector perpendicular to the plane. The initial question was, what is the equation of a plane? All right, so the equation of a plane is the vector perpendicular, which we call the normal, right? That's going to be dotted with a vector in the plane. So I'm going to go with the point A to the arbitrary point P on the plane. I'm going to draw a picture in a second. That's going to be 0, right? We have this plane. We have this normal vector, all right? We have the point A, which we're given, and then we have some arbitrary point X, Y, Z in the plane, and we're dotting the normal vector with that vector. This is a quick derivation of the equation plane. So our normal vector was -35, -49, 7, and we're dotting that with the vector AP. So XY, what was A? Let's go ahead and grab that. A was 3, 1, 4. So we have X minus 3, comma, Y minus 1, comma, Z minus 4. So you don't actually have to do all this extra work, this dot product that I'm doing, but I like to do it just to remind myself this formula and why it actually is the equation of the plane. All right, so we have -35 times X minus 3 plus -49 times Y minus 1 times 7, plus 7 times Z minus 4. That's equal to 0. And then I'm just going to simplify this thing up. What I ultimately get is -35x minus 49y plus 7z plus -35 times -3 plus -49 times -1 plus 7 times -4 ends up being 126. There is your equation of the plane. Using the cross product, and the dot product, but using the cross product to get the normal vector, and then using the dot product to get the equation of the plane. Yeah, so that's what I wanted to get to in this video. I wanted to define what the cross product was, and there was several requirements there. It needed to be perpendicular to the initial vectors. It needed to be a vector. It needed to have a specific magnitude, UV sine theta, and it needed to follow the right-hand rule. To find the cross product, we had to quickly introduce the determinant. I am 100% aware that I did not do the determinant justice, and you may be still confused of what the heck the determinant is and why it matters. But what was convenient was that it worked with the formula for the cross product. All right, so if we take I, j, and k as our first row, our second row the first vector, our third row the second vector, and we do this thing called the determinant, we will get the cross product, the vector that meets all those requirements. All right, so that gave us the formula. And then at the end, we calculated a cross product, but we also found the equation of a plane using the cross product to find that normal vector. So the cross product has a lot of powerful applications. Right? There are a few other applications like the area of a triangle or the area of a parallelogram that you could use the cross product to figure out, but I will let you guys do that in the problem set. All right, I'm going to close this video out. I hope you enjoyed it. There's the cross product.